The mean of this distribution is the population mean. The standard deviation of the sampling distribution of the sample mean is the population standard deviation divided by the square root of the sample size. We just went over intuitively why the standard deviation is smaller, and specifically the math is you divide the population standard deviation by the square root of the sample size. We'll stay on here for just a minute, so absorb that. So let's look at this notation in these terms. Remember, this mu means mean. But this mu has a little subscript with an x with a bar over it. All right, so that's read as mean of the sampling distribution of the sample mean equals true population mean. This is the symbol for the true population mean. And remember this little O with the funny hats? This is the population standard deviation. So this, the population, the standard deviation symbol with the little subscript x bar, it is read standard deviation of the sampling distribution of the sample mean equals population standard deviation divided by the square root of n. So let's read this one more time. Kelsey, what is this? Read this symbol to me, please.
The sample of the sampling distribution of the sample mean.
Equals what? Adamus.
Equals mean.
What mean?
Of the true population.
The true population mean. Fantastic. All right. And what does this symbol mean? Monica?
The standard deviation of the sample mean?
Yeah, close. The standard deviation of the
Sample, oh, okay.
sampling distribution of the sample mean. Yes. And that is equal to what? What is this symbol, Joanne?
The standard deviation.
Of what?
The population.
Divided by
The square root of the sample population.
sample size. Sample size. Little n is the sample size. Okay? We're happy there? This next slide says almost exactly the same thing with one little change. So the expected value of the sample mean, the mean of the sampling distribution of the sample mean is equal to the population mean. The standard deviation of the sampling distribution of the sample mean is equal to standard deviation of the population divided by the square root of the sample size. Now this guy here, the standard deviation of the sampling distribution of the sample mean, can sometimes be called the standard error of the mean, and can also sometimes be just called the standard error. Well, standard error. Actually, you know, that's a good point. I should just erase this middle part. It was just a step that you don't need. What I'm telling you here is this is sometimes referred to as the standard error. So if you don't feel like saying standard deviation of the sampling distribution of the sample mean, you could just say standard error.
We'll go with that. We'll go with the standard error.
Okay, that's all right. I mean, I think saying it out reminds you what it is. We talked about how the sampling distribution of the sample mean has a smaller standard deviation because the chances of outliers are significantly lower. Definition of the sampling distribution of the sample mean. Probability distribution of all possible values of the sample mean when the sample size of n is taken. That last line says for large enough sample sizes, the shape of the sampling distribution of the sample mean will be normal. And that's what helps us. Because if we know it's normal, we We know pretty much everything about it. 68.3, 95.5, this, that, and everything in between. What do we mean by large enough?
The larger the number, the closer we are to the actual population.
Yeah, so the larger the number, the smaller the standard deviation is, so the more precise of an estimate we can make. In terms of sample size, the sampling distribution and sample mean will be normal with a sample size of 30. Statisticians like 30. They say, okay, if you have a sample size of at least 30, fine. You can use all those normal distribution qualities. And they call this the central limit theorem, which just means as we get to a sample size of 30, the sampling distribution of the sample mean becomes normal. Now, if the parent population, and you may not remember this until we talk about it because it will be relevant next week, not this week. But if the parent population is normally distributed, then we don't even need a sample size of 30. We could have a sample size of 5 or 2, and the sampling distribution of the sample mean would still be normally distributed.
What do you mean by parent population?
Like all 10,000 Mercy College students.
Oh.
But if we don't know that the parent population, whether it's normally distributed, skewed, whatever, then as long as we have a sample size of 30, we're good.
So the central limit theorem, does that mean that the number of samples you take should be 30, or does it mean you have to do 30 samples?
30 sample size. Your sample size for any one sample should be 30. Now, the sampling distribution of the sample mean, it has like 10, I gave the example, it has like 10,000 samples on it. We're never going to do that in reality. And people don't really do that. I mean, grad students in statistics might do it for fun. But we won't do it in reality. We'll just know that if we did do it in reality, that's what would happen. So we now know that any one of our sample means, and we're only going to take one, we know that there's a 68.3% chance it's within one standard div, so on and so forth. Okay, so this would work if we're trying to find average income in a town in New Jersey that has a normally distributed income. Sampling distribution and sample mean would work. It would also work if this income distribution is not normal. Suppose we have a town with a skewed population, a skewed income distribution. The mean income is 80. It's still 80, and that's what we're looking for. And that's all we're trying to look for when we try to find the sample mean. We would take samples as long as they're 30 or above. The sampling distribution of the sample mean for this skewed distribution would still be normal. Any shape of any parent population. Here are a couple of weird shapes of parent populations. Okay. All right, think about the funny income distributions in these towns. Pretty much everyone is unemployed, and then we have a few people who have this entry-level job, and then there's sort of a promotion scheme where only, whatever, the best get more and more. Here we have like one factory in town that pays a little, one factory in town, or finance, building that pays a lot, and we've got some weird stuff happening in between. All of those parent populations have a mean, and as long as we take a sample of 30 or more, the sampling distribution of the sample mean will be a perfect bell-shaped standard normal distribution. Okay, that brings me to a specific example with confidence intervals. Let me just throw out this example and we'll discuss it. Suppose we want to estimate the average cost of an MBA program We take a sample. We find that the average cost is $43,000 and the standard deviation of the sampling distribution in the sample mean is 2,000. Please state the interval estimate for the average cost of every MBA program. Use a 95.5% confidence level. See if you can give me the answer to that. Your confidence interval is going to be two numbers. It's going to be between this 1,000 and this 1,000 number. And you're going to say you're 95.5% confident that the true population mean is in between those two numbers. Who has answers for an answer?
39,000 and 47,000.
I like it. Do you all like it?
I'm gonna like it a second.
Alright, I'll tell you how. The answer, let me just state how you'd explain the answer. You'd say I'm 95.5% confident that the true mean, the true population mean, is between 39,000 and 47,000. Here's how you know. This 43,000, that is a sample mean. It's a sample mean of a certain number of people, a certain number of programs, I guess. Not the whole population. This is a sample mean. You are 95.5% confident that this sample mean is within 2 standard deviations of the true population mean. Right? You are, right?
Yes.
Okay, so if you make your confidence interval 2 standard deviations wide, then it will include the true population mean 95.5% of the time.
Okay.
So if you want to be 95.5% confident, you make your confidence interval 2 standard deviations from your point estimates. So you add 2 standard deviations and you get up to 47,000. You subtract 2 standard deviations, get down to 39,000.
No, because your standard deviation is 2,000, so that times 2 is 4 plus
Yeah.
30, 47. Okay.
Yeah.
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 So you times 2
I got it without even.
there.
So you're going to stand up and say, I'm 95.5% confident. True population mean is between 39,000 and 47,000.
So that's, Professor, that's pretty simple. There's not a formula connected to an example like that. That's just adding the standard deviation, as many deviations.
Yeah, there is a formula, and what we did is we took the point estimate, plus or minus 2 times the standard deviation. Okay, the numbers that are going to change, all 3 of those numbers are going to change. The 43,000 is going to be something different when we do another problem. The 2 is, in this case, we wanted to be 95.5% confident, so it's going to change if we want to be more or less confident. And of course, the standard error is going to change depending on the outcome of the problem. Yes, Mike?
So why did we have to do the 2,000 times So,
We wanted to go 2 standard deviations above our point estimate and 2 standard deviations below our point estimate.
okay.
So one standard deviation is 2,000, and another one is another 2,000.
So you multiply.
So 95 of both sides, 95.5 is always going to be
Yeah,
plus 2.
Right, so if it was
Yeah.
one standard deviation, it would only be
Yeah.
2,000.
So it would be
And the
2,000.
reason it's
4,000 is $4,000.
Yeah.
Because the balance is this one.
What about if it's 85.5? What about if that's 85.5?
Well, we can do that one.
68%.
Well, let's do that one in a minute though. Remember that you want to know 85.5.
I mean, because that's just a number I know. How about if you throw 75.5?
Yeah, we can do both of those. So let's stick with the 95.5 for just a minute. So we're conducting samples. 95.5% of the time, that sample mean is going to be within 2 standard deviations of the true population mean. On this sampling distribution of the sample mean, remember what the mean of this distribution is? This mu symbol? What's this mu symbol mean? The mean of the population. Okay, this is what we are trying to determine. The mean of the population. We just have a sample mean at this point. We want to know how close it is to the mean of the population, this red line. So take a look at this little x bar 1. This is a sample mean. We added 2 standard deviations above it, 2 standard deviations below it. We said I'm 95.5% confident that the true population mean is between these 2 numbers. Are we correct in this particular case?
Yes.
Yes, because this confidence interval contains the true population mean.
Okay.
Take a look at what happened down here, x bar 5. That is our sample. Our sample was here. We added 2 standard deviations above, subtracted 2 standard deviations below, and we said I'm 95.5% confident that the true population mean is between this number and this number. Are we correct in that case?
No.
No. How often does that happen?
4.5%.
4.5% of the time. 4.5% of the time, we're going to come up with a sample mean that is a confidence interval that does not include the true population mean. Essentially, we're going to get it wrong 4.5% of the time if we only add 2 standard deviations. What if we don't want to get it wrong 4.5% of the time? We go 3 standard deviations. Alright, let's add 3 standard deviations plus or minus from our sample mean. This confidence interval would be bigger, and we probably wouldn't get it wrong. We'd still get it wrong maybe 1% of the time, 0.5% of the time. I don't know exactly what that is, 3 standard deviations. No, actually, it's 90. It's
99.
yeah, it's 99.7. So we would get it wrong 0.3 of 1%, 0.3% of the time, if we went 3 standard deviations wide. This is just the same thought process if our confidence interval were 1 standard deviation. So our sample mean is what we call our point estimate. That's our best guess for the true population mean. But we don't want to stop there. We want a confidence interval which is more likely to contain the true population mean. And not only that, we can say exactly how confident we are that it will contain the true population mean. So we're going to go sample mean plus or minus some amount. In our previous example, we wanted to be 95.5% confident, so we plus or minus 2 standard deviations, or 2 standard errors, excuse me, and whatever the standard error was. Here is our general formula. Sample mean plus or minus whatever we pick for our z value times the standard error. Remember these symbols here? Remember this population standard deviation divided by the square root of the sample size? Have you seen that earlier tonight? What is that?
Standard error.
It is the standard error,
Standard error.
also known as the standard deviation of the sampling distribution of the sample mean.
Right.
So we want to go plus or minus some number of standard errors. If we want to be 95.5% confident, we would go plus or minus 2 standard errors. Now what if instead of being 95.5% confident, we only need to be 95% confidence? How many standard errors would we need to plus or minus in that case?
1?
You're on the right track that it would be less than 2, but 1 is not the correct answer. We're gonna need to look in the Z table.
So it'll be like 1 point. I want to say like
Take a step.
1 point.
1.8?
Oh, some.
1
I
point
want to say
something?
like 1.7.
1.7?
Somewhere around.
1.76?
1.76?
95, you said?
95% confident.
1.75.
1.65.
Okay,
Alright,
I like.
so 1.7.
Alright, those of you saying 1.65, you're absolutely on the right track. You look on the Z table and you're looking pretty much for the right thing, but there's one little nuance you need to be aware of. Okay. So if we're going to be 95% confident, it's going to be a little less than 2, for sure. 95% confidence means we get it right 95% of the time. What percentage of the time do we get it wrong?
5%.
Still 5%?
5% of the time. There are 2 ways we can get it wrong. We can get it wrong with a really high sample mean or a really low sample mean. We end up just talking to too many rich people, we end up talking to too many poor people, just randomly, it happens, 5% of the time. So there is going to be 2.5% of the time where we will talk to too many rich people and get too high of a sample mean. 2.5% of the time where a sample mean will be too low. So for 95% confidence, we need the Z value that separates the upper 2.5% from the bottom 97.5%.
Are you looking for a Z value of 5?
We're looking for the Z value
1.65?
that separates the upper 2.5% from the bottom 97.5%. So this would be a Z value with 97.5% of the area under the curve.
So it's 1.96?
1.96 is the correct answer. You look in the center of the Z table for 0.975. You put your finger on that and you say, what is the Z value here? 1.96. So we would plus or minus 1.96 standard errors, and we would stand up in front of the conference and say we are 95% confident that the true population mean is between these two numbers.
So we're not looking for the 95%, we're looking for the.
2.5 up here, 97.5 down here. You just need to draw a picture and think it through each time. Now, Carol asked earlier, what if we wanted to be, what did you say, 85% confident?
Yeah, just another number, 85.5.
Okay. 80, let's do 86, just to make it easy, right?
Okay.
Want to be 86% confident? Okay, so what percentage of the time are we going to get it wrong? 14% of the
So it'll
time.
be 7 and 7.
And since this is normally distributed, we know that there's even probability in each tail, 7% up here, 7% down here. Okay, so we're looking for the Z value that separates the upper 7% from the bottom 93%. So look in the center of the Z table for 0.93.
0.93.
For 7%?
For 84% confidence,
1.48.
84% confidence.
So it'd be 14.
I thought we did 86.
Yeah, sorry.
So it'll be 1.48.
1.48,
Yeah.
Yeah.
is that right?
Yes.
I don't know, I've never, I don't have that one memorized, 86 is. The common confidence intervals are 95, 90, 95, and 99. Alright, so it's 1.48?
Yeah.
Okay, so we add and subtract 1.48 standard errors to our point estimate, our sample mean. We have a bottom number and an upper number. We stand up in front of the conference and we say, I'm 86% confident that the true population mean is between these two numbers. Make sense?
Makes
I
sense.
didn't get it. I got lost for a moment. So, okay, I get how you got the 7 because that's dividing that 14% on
Yeah.
each side.
Yeah.
Then I'm lost after that.
Okay, so this is just the normal distribution with 7% of the data above it and what percentage of the data below it? How much is below it? 7% is above, how much is below?
The 93. Okay.
93%. 0.93 is below here. So now you're looking for a z-value that has 93% below it, 7% above it.
Oh, I
Wendy? Smile because it's funny? You can smile because you get it or because it's funny. I would take either. Yes, Joanne?
Yeah, you had the 1.48.
Yeah, so you take 1.48 standard errors, add that to your sample mean. 1.48 standard errors, subtract that to your standard error, subtract that to your sample mean. Then you've got your confidence interval.
Maybe 86%.
Now, there's a formula here you could use to calculate the z-value. This will work, but I don't suggest you start here. I suggest instead you draw a picture and think it through just like this each time. Let's try an example or two. I think that may shed some more light on this. Let's take a look at page 248, number 20.
I think the exam we do have to come to class. So,
No, I did it in exactly because I started turning. Oh, so February, so year and 3 months. But I did 3 and 2 and 1 and 2 and I gained 1 class because I'm a transfer from
And they're gonna accept it? I got a fight.
You can kind of see that, right?
And she was like, well, you know, because they already weighed to that. I'm not, I'm gonna fight for her. She's one person. Absolutely. It's a financial statement. How is
Yeah,
that
I was
like?
just looking at the computer.
You don't need it, but I mean, that could take off from my elective. I started online. And then I just changed my whole concentration. And I was gonna do accounting. That's what my undergrad was in. And I wanted to do marketing. No, marketing.
Oh, okay.
Everybody has to take it. You give that Khan Academy and Turbo, like, no. Really. Enough already, like, we got it.
Your marketing's completely different.
I know.
I'm writing down.
I would never take it when I finished turbo, but I was like, I had enough already. I didn't wanna see no work, I'm like.
Don't like when
I know.
two of them.
Yeah, I just barely pass with some last time. That was one, but people diversity. Marketing was the products, new product development, but I had like some family emergencies, so I was just out of it. Yeah, I'm doing
I want you to find the Z value that's
business concepts, like
one that separates the upper
human research,
2.5
something like that. I'm
and bottom
doing
97.
management, business concepts. I'm doing that one.
You need to find the Z score that has 97.5%.
I know, but you give me 3 more. Like, I need that.
Because I think
I still have to do one thing.
No, because 5% chance of error, 2.5% in our year two.
No, but I
The 5% chance of error could happen 2 ways. Yeah.
No, but that's the thing, that's not.
That's the way we present. I know. 16 projects. Yeah, who has the freaking time to do 16 projects? I have to drop
So
it.
we have a this is
I
normally,
hate
this is sample
14 projects,
distribution,
but
sample
when you
means
tell me
normally
I'm being
distributed,
assigned
because
to
it's
stuff.
normally distributed, we know all this stuff. So 2.5% of data is in the upper table. How much is that in the lower? No.
Of course. I was at 20% last quarter.
So what's 100% minus 2.5%?
What was in the 20?
That you did the work or you didn't?
None. I did not.
Maybe where you're getting confused.
I
is you
have
think we don't
family
want to subtract this
issues
off.
that I just,
But the
I
way the
was
Z
really
table
really out
reads,
of it.
is
I mean, you know, just part, they did the outline and I just read and threw it away for good measure. And it was, you know, we got it. I was like, the only time I got
you
like
want to
full
know
credit
the
for
Z
something.
value that has 97.5% of data
I was good at facilitating our communication, like that was my input on it as far as getting us all, you know, on a group chat and then we communicated that way.
So there would be 95% in
But I
between
used to
those
just
two.
do one
There'd be
class per
2.5%
quarter.
in either two.
Now I'm doing two.
So you times this by 2 and then add it and then
But
subtract
this is,
it?
I didn't want to do it a year, I said 2 years is okay.
Right.
You feeling good, John?
No, not at all, we were not.
You're talking about something else, that's
Turbo, I give turbo and finishing and all that.
Turbo's over, right?
Yeah, yeah.
Good job.
This is the,
So how do we know this like?
this number 10.
Z. Okay, so you've got the 8.2 is your point. Yeah.
That's my
Yes. Reading Z.
And then,
And you know how to put it sampling error just like that. So that's the, whatever. 2.6 divided by the square root of 754.
Okay.
So that part.
So then let's look at that, the height, right? Plus, so do I use the V here, the 196? So this is zero.
Oh, okay, so no, the mean is what we have.
Right, that's why we add subtract the rate.
It's
That's the answer.
Right. So, no,
no,
remember the mean is what we take, see, like here, the mean is taken here, times the time, so.
So what I was doing here, I went back and
No,
used
not
this
the
formula
mean.
to do that.
Right, oh, okay.
But that's where I'm confused at, because if we have this number, but this says the standard deviation is this, so that's where I'm at.
This part, we're gonna have to find out.
Yeah.
So you at? That's the mean.
1.9.
Yeah, so that's the number we add in, or subtract into.
So we're just gonna plug these in.
Yeah, that's right. Yeah, that's square root of it. Square root of it.
These score 95%.
Square root of it. All right, should we do this together?
Yeah, we have.
Yes. All right. So in this case, this organization is trying to find the average time teenagers spend online. This is important stuff, right? I mean, how much, like makeup teenagers buy, how many, video games teenagers buy, what else do teenagers buy? So the more time they spend online, we may be able to market our stuff to them. So this group surveyed a random sample of 754 teenagers. They found the average time these teenagers spent online was 8.2 hours. They know that the population standard deviation is 2.6, and they want a confidence interval for the true population mean. All right, so that is the average amount of the time that every single teenager spends online. So that's a lot of teenagers, right?
Yes.
And they just asked 754 of them. So let's get that confidence interval. We need the point estimate of 8.2 plus or minus, remember some z value, times the standard error, which we know the formula is the population standard deviation divided by the square root of the sample size. So let's find that standard error. And actually, before we find that standard error, somebody read this to me. What's the long name for standard error?
Standard deviation of the sampling distribution of the sample mean.
Yes, perfect. And that is calculated population standard deviation divided by the square root of n. So that's 2.6 divided by the square root of 754, which equals what? 0.09?
I got 0.094.
Yeah, okay. So about 1/10 of an hour, very close to 1/10 of 1 hour. 0.094. We like that for our standard error. We just crunch these numbers, and we've got a standard error. So in this spot right here, we're going to put 0.094. Question is, how many of those standard errors plus or minus are we going to go? Well, if we want to be 95% confident, same thing we did a minute ago, but I'll just do it again. If we're 95% confident, what percentage of the time are we going to get it wrong? 5% of the time. That 5% of wrong answers is going to happen two ways. Sometimes we're gonna get a really high sample mean, sometimes we're gonna get a really low sample mean. So we divide that 5% by 2. We find that 2.5% of the time we're up here, unfortunately. 2.5% of the time we're down here, unfortunately. So what I need is the z-value that separates the upper 2.5%
1.96, I think.
from the bottom 97.5%. So that's 97.5. It includes the 95% in the middle and the 2.5 in the tail, for a total of 97.5% area under the curve for this z-score. What is this z-score?
1.96.
1.96.
Perfect. Alright, so we're going to erase this, and we're going to put in 1.96 times 0.094, and we're going to do the math to calculate that for our confidence interval.
Thank you.
Does anyone have either of those, the upper or lower bound?
Oh, multiplication, okay.
I'm not liking 10.04 because...
8.38?
What's that?
8.38?
8.38 for the upper bound, I like that.
Oh,
Yes. 8.38. Got
You
it.
add it, you add it.
8.02.
8.02. Okay, I like those. Because what's happening, this standard error, it's only 1/10 of an hour. That's pretty close, right? That's pretty tight. We're able to get within 1/10 of an hour for our standard error. So to be 95% confident, we only need to add 2/10 of an hour and subtract 2/10 of an hour. We get a lower bound and upper bound. And then we stand up in front of our investors, and what do we say?
You're 95%.
we will be between 8.02.
If the plus or minus.
We're 95% confident that what?
That gamers spend about probably
Teenagers
right.
spend,
Teenagers spend about 8 hours to 8 point. I mean, those numbers.
yes. So we stand up and we say, I am 95% confident that teenagers, the average time teenagers spend online is between 8.02 hours and 8.38 hours. So what's that, about 8 hours and, between 8 hours and 8 hours and 20 minutes? That's a pretty darn close estimate, isn't it?
Yeah.
And they're 95% confident that that is the true population mean out of, I don't know, 50 million teenagers? Yes, Ron?
Shouldn't that range be somewhere close to, I know it's not exact, but close to 2 standard deviations one way or the other?
Yeah?
Or it's nowhere near that?
This is the standard deviation. This is
Standard deviation was 2.6.
of the population.
Oh.
The cool thing about the sampling distribution sample mean is that it's a tighter standard deviation. Because what are the chances that all 754 teenagers give us a really skewed result? Tiny.
You don't have to break it up.
You want to look at it? Here you go. Just don't touch the egg, this is fresh.
So let's go, why don't we go to 22? Let's do 22. 22A and B. Are you with me?
Yes.
Yes. I won't give up on you. You don't give up on me. Or you're safe. How's that? Yes, ma'am.
Anytime you're talking about confidence intervals, you're talking about the distribution of the sample mean, not the sample itself. Right?
Not the population. Yeah. 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 If you're talking about confidence intervals, you can rely on the sampling distribution of the sample mean. Because you can assume that that is normally distributed, and you know things about it as a result.
Which number you want to do?
22. Let's do 22.
Right, formula.
All right. We're close to the finish line. You're doing great. 22. Yeah, change my mind.
Do 22? Yep.
Are you using Excel? Yeah, use Excel.
Yeah, because
For the long run, should be more, like, more features should pop up. Or no reason.
I might have turned it off like I think I did actually.
Square root of 200. See, that's what's supposed to be like.
Oh wait.
14.
Oh, okay. No, I messed up. Yeah, yeah.
That calculator must be using it on a cell phone, right?
Yeah. The cell phone last week.
How you make it?
I'm messing up the math.
Let me show you what I did.
196.
Yeah, because it's 95%, so it's the same.
Where are you good?
Yeah.
This part.
So this is the form.
Like that, and that's what you.
No, I know the
The
form.
plus and minus, that's not.
So that's where this is.
Good job.
Oh, wait, you already,
Plus, right.
okay, never mind. I thought you did.
So the square root of 200 is 14.1.
Yeah, you better just get rid of it.
And then 5,800 divided by 4.1 is 482.
What you reckon about it, right?
Right, that's that.
That's the square root you just did.
I'm gonna do 1.96.
So 14.
So it's the same number.
And then that's when you do plus that number. I thought I was right last time too.
Yeah, and then.
I got 480.
61.98.
Yeah, no, alright, now 42.
Teachers,
99,
average
right?
salary for teachers in California. Yeah,
Alright, cool.
59,000.
What's your number?
You wanted us to do A and
Yeah.
5, 3.
Okay.
B?
And then we just add and subtract.
95% confident and average salary for teachers.
Actually, we'll just start now, and we'll do B together. All right, are we ready to do this together?
Right.
Yes.
Let's do it together. Wherever you are, just consider that good night's work. No more calculations for you. All you need to do is watch, relax, and absorb. So we are trying to determine average teacher salary. And for some reason it's in California, I guess. Average teacher salary in California. For some reason it's difficult to survey and get information on every teacher in California because it's all political there and school districts don't want to tell you. They're trying to, I don't know, for whatever reason it's difficult to sample to test the whole population. So we sample 200 randomly selected teachers. We find a sample mean of 60,583 out of those 200. We know the population standard deviation is 6,800. So our confidence interval is going to be our 60,583 plus or minus some number of standard errors. Let's calculate our standard error. Now the great thing about this standard error is it is less than the population standard deviation. So we don't have to go plus or minus 6,800 2 times. That would be crazy. Because we're using good sampling techniques, we can make that a smaller standard error, tighter confidence intervals. What do we get when we take 6,800 divided by the square root of 200?
48.83.
480.83 sounds right to me. So that is our standard error.
No, I didn't get that.
Next question is how many standard errors do we need to go, plus or minus? 1.96. If we want to be 95% confident, we go 1.96 standard deviations. We calculated that in the last example. So 60,583 plus or minus 1.96 times 480.83 is going to give us our confidence interval. If you know the lower bound, just scream it out.
59,640.57.
6,041?
40.50.
40?
Yeah.
Okay. Okay, let's just leave it at 40. Okay. What's the upper bound?
61,525.
585?
525.
525. Okay. 525. Who would like to do the interpretation?
Kelsey does.
What happened?
That's all, but it's still coming to the same thing.
We need the second one?
Yeah, the interpretation.
We right on, we just gotta change.
Monica?
What?
The interpretation.
The interpretation.
Oh, I wasn't raised about here for that. We're 95% confident that the teacher's salary in California is between 59,640 and 61,525.
And I have one issue, you said the teacher salary, we're confident that the what?
What was it? The average salary?
Average teacher
Average
salary
teacher
in
salary.
New York is between, or California, is between 59,640 and 61,525.
Yes.
That's pretty close, that's within, what is that, 2,000?
Yeah.
Yeah, so we're 95% confident, that's just asking 200 teachers out of 50,000 teachers in New York, or California,
I
sorry.
don't know how they got 4.
Alright,
So now if it's
Let's-
99,
let's figure out, for the 95% confidence, we needed 1.96 standard errors. Let's just figure out what that would be if we wanted to be 99% confident. And then we'll leave it at there. We won't do the full calculations. Just say, what would this be if we wanted to be 99% confident? If we're 99% confident, what percentage of the time are we going to get it wrong?
0.5, well, 1%.
Yes.
1%.
Yes, you're right. We're going to get it wrong 1% of the
1%
time.
Yeah, sorry.
And then you're right. You're right.
And divided by 2, and then we look at a C table.
Yeah, and that means 1/2 of 1% of the time we're going to get it too high. 1/2 of 1% of the time we're going to get it too low. You with me there?
yes.
So we want the z-value that separates the upper 0.005 from the bottom 0.995. So below this z-value is 99.5% of the data. Above it is 0.5% of the data. What is that z-value?
2.58.
2.5.
How do you know if to go with 5.7 or 1.3?
Because you want to go over.
I like to
You wanna
go
go
with the
over.
one further from 0.
Right.
Either one would be acceptable though.
Yeah, ready.
The one further from 0.
Okay.
2.58. We would just plug 2.58. We'd get a larger spread, but we would be much more confident.
Okay.
Great work. Look forward to seeing you next week. You should be awfully proud of yourselves for chewing up this material.
Is there sign sheet?
That was tough for
No, no sign sheet.
Only the first part.
I hope it doesn't get much harder than
It doesn't get much harder. It gets easier than this, and I would say it especially gets easier than this if you understand this material.
Okay.
If you don't understand this material, then it gets much, much harder.
This is more
So please
mental.
take this week,